Okay, here we go. Welcome back. Happy Friday. Today we cover distribution functions and probability. This is our last day of new material before the second test. Coming up Monday is our review day. Also coming up Monday, Project 6 is due. So a lot of folks in the studio that have made very good progress. I think some people are just about finished or all the way finished with that, which is great. That's due on Monday. Monday is our review day for test number 2, which is scheduled for Wednesday coming up. Test number 2 is on all the stuff since test number 1. So everything in here. I'm not going to go out of my way to test any of the material from the first test, but you still have to know how to do the stuff from the first test. So for example, even though substitution was technically a test 1 topic, you still need to be able to do U substitutions on our test number 2. Okay? Any questions on the calendar? Okay. Then let's jump in here again, top of page 68 with our daily summary. Can we go to Petru? Okay, so number 1 says we're going to talk about this age distribution example, which is in your textbook. So let's just look at our, I think it's called a histogram, right? So this diagram over here on the right-hand side, which says that that 29% of the U.S. population is between 0 and 20 years old, and 31% is between ages of 20 and 40. Everybody understand what that histogram is telling you? The info in the chart is just, it's the same, it's just a visual way to see it. Okay, so let's move on to number 2 here, and we'll go to Steve. Okay, let's do the 20 to 60 first. What percent? 55%? Everybody okay with that, right? 31 plus the 24, so this is 55%. Fair enough. Between 75 and 80, is it half? It's a quarter, right? A quarter, 5 years is a quarter of that 20-year block. So the only estimate we can make is cutting it into a fourth, so 13/4, right? What's that?
All you can do.
Yeah, that's all that we can do. But then we're going to decide whether that 13/4% is an over or underestimate. And I think we'll be able to agree on whether that's too big or too small. Well, let's jump to part C first. Between 80 and 85 years old. So 3/4, right? Because 3% is the whole box. So 3/4%. Everybody okay with that? Okay, but then in number 3 here, it says decide whether each estimate was an over or underestimate or can't be determined. So the first answer, the 55, if we trust the picture, then the 55 is perfect. I mean, like that's exact. So it's really about B and C. So we know that between the 60 and 80-year-olds, that's 13% of the US population. But what do you think? Is it an exact number of 61-year-olds, as 62-year-olds, as 79-year-olds? There's probably more 61-year-olds than 79-year-olds. So do you think this 13/4 is too big or too small? It's too big, right? Because really there's that 13% is shifted to the left. So this is too big. And then how about the between 80 and 85? We said that was 3/4%. That's probably too small because the number of 81-year-olds far outnumbers the 99-year-olds, right? So this is too small. So if we wanted to be able to say things with more certainty, what would you like to do with that picture if you could like change it in some way? Yeah, like smaller chunks, right? Which is kind of starting to feel like what we've been doing for a while now. So down below is another graph with smaller chunks. This one goes every 10 years instead of every 20 years. So we could say more accurate answers in this picture. And then if you imagine, what can we imagine? If we imagine smushing down farther and farther and farther, making really thin rectangles, like here's how many people are exactly 22 years old and 183 days, then you have these razor thin rectangles, but really accurate information that you can get. And so if we just scrunch them down forever, then that blue curve there is kind of the limiting value of the age distribution, right? So instead of a histogram, which is by nature just an estimate, the curve is like the theoretical perfect way to think about how people are distributed age-wise. All right, so that's fine. So let's go to the next page. And we'll define this thing called a density function. Gabe? Okay, let's pause there. Would you guys buy that, like, if I look at the curve itself and I find the area under the curve, then that's the percentage of people that are between those years, right? Even if it's not a perfect rectangle like we were doing, it's just area under a curve now telling us the percentage of the population that's between ages blah and blah. And so that's all that it says here, that the fraction of the population between ages A and B is just the area under the curve between A and B. Okay, but then there's this other piece. It says that the integral from minus infinity to infinity of p of x. P of x is that curve we were just looking at. What does that have to equal? It has to equal 1, because it's got to have an area of 1, because it's 100% of the population is somewhere, right? So someplace under there you have to live, and you're not going to live there twice, and so it's got to be an area of 1 or 100%. The minus infinity to infinity, okay, so our age example, like probably like 0 to 150 will capture everybody that has ever lived, right? But in, like in theory, could have stuff that has negative values, not age, but other things could have negative, could have positive, could be really big or really small, so we'll just capture everybody with the minus infinity and the infinity. And then the other piece is that the percentage of people living in a certain spot has to be at least 0, right? You can't have any negatives and be talking about probability. And so that's what this is saying the function is at least 0 everywhere. This fancy symbol here just means for all, upside down A for the word all. So P of x is always bigger than or equal to 0 for all x. Len, did you have a question? Okay, let's take a look at number 6. Len. Okay, so PDF no longer stands for the kind of document that you get out of Adobe. It is a probability density function, okay? PDF. And so here's the picture. This is, it's not the same age example, but this is just a probability density function. It's up there at a height of C when the value of the input is 0. And over here, when we get to 4, then the probability density function gets down to 0, and it's 0 from there forever. Can anybody think of an example where there's like a large number of things that have a value of 0, and then a decreasing number of things until we get to a value of 4, and nothing after 4? Anybody think of an example where the only allowable range of numbers is between 0 and 4? Juice boxes at lunchtime? If you never have more than 4 juice boxes?
Well, or C is the number of juice boxes.
None left. I don't think that's quite what C represents, but I do like juice boxes, so I appreciate the example. Seamus. GPA. GPA is between 0 and 4. Perfect. So what this is saying is that the most popular GPA is, what's the most common GPA? 0, that's the highest one, and the least common GPA is 4. Okay, so, but it's still that's the right idea. Is that most people are getting 0s, lesser and lesser people getting 1s, 2s, 3s, and hardly anybody getting, like in theory, nobody getting a 4.
Is this the curve of GCC?
No, it is not. Not. Okay, so let's find the value of C. The only thing that we know is that the total area has to be what magic number every time? Has to be 1. So we just need 1 to equal this area. So the area is equal to half the base times the height. Half of the base is 4, we'll do half of it. And then the height is C. Okay, so then the area of this guy is definitely 2C, but we need that to equal 1. So C had better be half. Okay, moving on to number 8. Cameron. Okay, so brand new definition here. There's this idea of a cumulative thing. So suppose that I'm just going to do a quick graph right here. Suppose that we look at our GPA example from up above. This guy turned out to be a half up there at the top. And then we look at down here is going to be the total number of people. Sorry, that's not right. Down here is the GPA, and over here is the total number of people up to the GPA, whatever number we're at. So if we start at the beginning here, we've got lots and lots of people with GPAs of 0. I'll just make up a number. Can't quite be right. We've got lots of people with a GPA of 0, and then fewer and fewer people with a GPA of 1, but we're just doing a cumulative thing. We're just adding people on top of this list. So maybe something like that. We're still adding, but not adding as many. And then people with a GPA of, so those are my 1 people, and these are my 2 people. These are my 3s. And by the time we get up to 4, when we're up there at the 4, what can you say about the percentage of people that we've seen? That's 100% of the population, right? Because we captured everybody by the time we get up to there. It's got to have a limit of 1, and then once you're up there, it's just flat. We're not adding any new people. It's usually just an approaching. In this case, because when we got to 4 on the blue curve, it was 0 forever, we actually did get to the value of 1. Okay, so this guy right here is called a cumulative distribution function, or CDF. And so all it's saying is take a look at the integral of the blue curve, the PDF, from minus infinity up to some number, just some varying number. And then we're just going to graph the total area up to that point, right? So we're going to have 0% at the far left, 100% by the time we get to the end of this at the far right, and then in between we'll get from 0 to 100. Okay, so let's try number 9, which says to sketch the CDF of the following PDF, and first we need to find the value of little c. So there's the picture. Oh, one thing. This is unfortunate notation. It's not my choice. This is what your book uses. Little p is the blue curve. Capital P is the red curve. It's the same P, but it's lowercase and capital, okay? So lowercase is our probability function, and then the capital P is the cumulative function. Okay, taking a look at this picture right here, how are we going to find the value of C? Area of that, and what does it have to equal? Has to equal 1. So we're just going to find the area and make sure it's equal to 1. So the area equals, okay, what's the area of the first rectangle? 1.5 times 2c. And then the area of the second rectangle? 0.5c. So we get 1.5c. And we always know that the area under a PDF has to equal 1. So that means the value of C is 2/3. The C, I don't know that it actually gives you anything useful. It's just a number that's on the y-axis someplace. Just to give us an exercise to make sure we understand the 1 idea. Yeah, I mean, like, no, there's no magical. I mean, look, C isn't even the top value in this curve, right? A 2C is the top value in this curve. And if you, yes, yeah, so do you guys remember the Laurent's curve? We line everybody up from the poorest person to the richest person, and then we would cumulatively, like, list them, right? Their total combined wealth. And so that cumulative thing, starting at 0, getting to 1 at the end, is the same characteristics we have here. That's a good connection. Mm-hmm. No, I think C is just something for us to play with. Look at the numbers here. They can have nothing to do with anything. Like the numbers here will be very different for another example we do today with fish. It's just completely dependent on the problem. Okay, so let's. All right, so let's actually find our cumulative distribution graph. So let's fill in. So C we said was 2/3. So 2C therefore is 4/3. So those are our y values. And now all we're going to do is sketch our CDF. And I'm going to put over here the same 0.5 and the same 1 that we had before. Okay. If we go to 0, then we haven't counted anybody yet because this graph doesn't exist to the left of 0. So automatically that point 0, 0 is our first point. By the time we get to 0.5, what fraction of the population have we seen already? It's 2/3, right? It's the area of that first box is half of the 4/3 height that we see. So the area of that box is 2/3. So 2/3 of the population is in that box. The remaining 1/3 is in the other box. So what we need to do is by the time we get to a half, we need to have seen 2/3 of the population. Super, we can do that. 2/3 of the population. So we'll put 2/3 maybe there. And so by the time we get to a half, we will have seen 2/3 of the population. And then do you buy that as we gain people underneath this horizontal line, we're just going to go straight line between my 2 red dots? Is that fair? We're just gaining people at a constant rate, so it's going to be a constantly rated. Normally it's a curve, but this case it's just a line because it has a constant growth rate. Okay, so that's good there. What's the slope of that line? You can do the calculation if you want. We don't need to, but we can. It's not 1/3. 2/3 divided by half. It's 4/3, right? Slope of that line is 4/3, which makes sense because that's the rate of change. That horizontal line at 4/3 is telling you every step you take, you're gaining 4/3. It's Friday. All right. Okay, and then the next thing. So then as we go from 0.5 to 1, what percentage of the people did we say is in that box? That's 1/3 of the population in there. That's the area of that box. So we need to gain the remaining 1/3, but we're going to do it over the course from 0.5 to 1. So what's the height at 1? It's 1, right? Because it's just 1/3 more than the number that we had before. And that 1, of course, makes sense because that's everybody. So out here, or there. And so just to highlight, so the slope we said there is 4/3. How about the slope of this second piece? Slope of that one is 2/3. We're not gaining people as quickly when you're out there. Rate has changed. Okay, So that is a cumulative distribution function. Okay, let's just fill in a few blanks and then you guys will move to the activity. P prime of t. P prime of t, yeah. Let's go back up to our definition. It's at the top of the screen here. Taking the derivative of this guy. Does that look like something we've seen before? It's P of t. Do you remember the name of this theorem?
Second fundamental theorem.
Second fundamental theorem. Remember it? Is that exactly the derivative of something that looks like that? Integral from a number up to x. Our number in this case is minus infinity. X is a t at the top, and our trick was just to change the variable inside the integral to that top letter, right? So this is just P of t. Small p of t. Which actually we verified here. This red guy, is this capital P or lowercase p? This is capital P. What is the derivative of this red guy from 0 to a half? It's the 4/3, right? What's the value of every number in little p between 0 and a half? It's 4/3. So the slope derivative of the one guy is the function value of the other guy. Okay, P is monotone. Your choices are increasing and decreasing. Monotone just means forever doing the same thing. So is the red guy always increasing or always decreasing? Always increasing, right? Because it's a cumulative thing. So you can't ever go down. You're always gaining. If you take the red guy, capital P, and you go forever to the right, what number will we approach? 1. That's 100%. If we go the same thing but forever to the left, 0. So we get every number between 0 and 1, increasing the whole way, just like the Laurent's curve in the Genie project. Okay, so last thing is 11. Let's go to Seamus.
X minus b squared is a 2 where mu is
That's right. So you guys have seen the bell curve before. I've drawn a real quick sketch over here on the right, right? High in the middle, low on the end. So that's the bell curve. And lots of things that we measure look like that. So like if you took the heights of everybody in this room, we would find that a lot of people have a height that's like 5'7". I'm just going to make up a number. And then there are a few people that have a height of 5'3" and a few people that have a height of 6'0", but we're all kind of clustered around each other someplace, say 5'7", right? No, this is the normal distribution is symmetric on both sides of the middle. So that's the idea. Is that lots of things that we measure look like that, and so there's a whole like books about that particular curve, so you can learn a lot about a lot of different things you can measure by just learning about this one curve.
IQ test.
Yeah, IQs are also, you know, right? Like everybody's, not everybody. Like I think the average is.
People are super smart, and people are really not smart.
Right, but most of us are just right around the middle, clustered around 100. Okay, good. So the activity starts on the next page. I would love for you guys to just make one small change for me. Can you go to page 72 for a second? Page 72. And you guys see this picture near the bottom on 72? And you see this formula right here. It says approximately equal to that stuff. Can you, as the best of your ability, not look at that formula? Cross it off? You're going to be building that formula in the activity, but we didn't realize that it was in the picture, the answer to the activity. All right, raise the flag if I can help.